Everybody, my name is Charvi Banor. Today, my team and I present a review of recommendation system algorithms. Here's the agenda for today. I will be starting with the a priori algorithm. So, what is the a priori algorithm? The a priori algorithm is used for finding frequent item sets for a Boolean data mining association rule. The name a priori comes from the word prior, as it requires the prior knowledge of the data sets that's being considered. Um, the a priori algorithm is mainly used to solve the market basket analysis problem. So, what's the market basket analysis problem? So, basket analysis is basically a data mining technique used by retailers to increase sales by better understanding customer purchasing patterns. So, Walmart did a survey where it went ahead and found out that if a customer bought cookies, he went ahead and bought a bottle of milk. To understand the a priori algorithm, one of the main concepts, the a priori property, which mentions all subsets of a frequent item set must also be frequent. But to understand it, we'll need three important formulae, which is the support, confidence, and lift. So support is basically the default property of any product. So if A derives B, then support is the frequency of A and B divided by the total number of item sets. So next formula is the confidence, which refers to the possibility that the customers bought both the products, which is defined as the frequency of AB divided by the frequency of A. Lastly, we have the lift, which refers to the increase in the ratio of sales, which is given by the support divided by the support of A into the support of B. Let's look at some statistics right now. So the time complexity is O of 2 power D. Practically, its complexity can be significantly reduced by pruning and using other optimization techniques. But however, the time complexity still remains O power 2D, where D is the total number of unique items. And when we consider space complexity, we know that the first step is used to store DC1 item sets, second is used to store DC2, third DC3, and so on until DCD. So when we sum the above terms, we get 2 power D minus 1, which is O of 2 power D. Let's look into the working. So if we consider the following transaction, T1, T2, T3, T4, and T5. In iteration 1, we calculate the support for the item sets with size 1. And here we see that 4 has a threshold which is less than 2. So we discard the value 4. Then we move on to iteration 2, where we calculate the support for item sets of size 2, and we discard any item sets with threshold less than 2. When we move to iteration 3, we consider a process called pruning, where we discard all the subsets which do not have the item sets present in the previous iteration. We are left with two item sets, 1, 3, 5 and 2, 3, 5. When we move to iteration 4, it has only a single item set of size 4 with a support value less than the threshold. So we stop the process over here, and the final subsets are 1, 3, 5 and 2, 3, 5. We can move on and find the confidence, which is given by a support of I divided by support of S. Here we see that the confidence of 1 and 3 and giving a possibility that 5 may also exist is 66.66%, which is greater than the threshold confidence value. So hence rule 1 is retained. However, we see rule 5 and rule 6 has been rejected. This is a comprehensive literature survey that I have neatly tabulated, which shows the optimization of a priori algorithms. Another novel application, according to me, which I believe can be implemented for the a priori algorithm, is the data corruption detection, where each dimension in the data set is considered as a unique item and the association between multiple dimensions can be calculated, resulting in a unique outlier or anomaly score or a threshold to detect if the data was corrupted or not. Such an algorithm has not been worked on yet and is something that I am working on and I would love to pursue. This is my implementation of the a priori algorithm using the a priori library from Python, which has the item sets. I've done a pre-processing and derived association rules, as you can see over here. Then the rules generated along with their confidence and lift is also being shown. Thank you so much. I now hand it over to Chaitra.
Hello everyone, I'm Chaitra Bhatt and I'm going to explain the matrix factorization algorithm. It's a class of collaborative filtering algorithm used in recommendation systems. As the name suggests, it works by decomposing the matrix into the product of two lower dimensionality rectangular matrix. Let's understand this with a real world scenario. Let's assume a Netflix universe with 4 users and 5 movies. How do humans behave in general? The matrix in the left has uniform values for all the movies by all the users, which is quite unrealistic, whereas the one in the right resembles the real world situation. Also, one more point to note here is that in general, the matrix is going to be a sparse matrix as a user not necessarily have to watch all the movies. As I said, the first step is the rating of the movie. The second step is to identify the dependent rows and dependent columns. Like the one here, the row A and row C is same, that is, Anna and Carlos have a similar taste. Again in the right, movie 1 and movie 4 have the same ratings. Some more observations are row B, row C add up to row D. Again, the average of movie 2 and movie 3 rating is going to be the rating of movie 5. But the main question is, in a huge matrix, how do we figure out these dependencies? The answer is matrix factorization. So our task is to come up with two matrices, say this and that matrix, which is gonna yield the original matrix on multiplying. This is done with the help of features. For example, Anna loves comic movie, but then she doesn't like action movies. At the same time, Male Cop is a movie which is rated 3 in terms of comic and 1 in terms of action. Anna, being a comic lover, at the same time, Male Cop being a comic movie, she's gonna love the movie and rate the movie as 3. In a similar way, Betty loves action movies, but the Male Cop is poor in terms of action, so obviously her rating is gonna be 1. Using all these, we come up with the two matrices, that is this and that matrix as I've mentioned below. On multiplying these matrices, that is this row with this column, you're going to yield the value of the first box, and similarly you can fill the rest boxes. The one advantage of it is that the dependencies are clearly visible when you factorize than when you can figure out in the original matrix. The second major advantage of decomposing is that in terms of storage. So if you maintain the original matrix, that is the 1000 movies and 2000 users, it's going to have 2 million entries. Whereas when you decompose, it's going to be 200k plus 100k, that is 300k entries, which is far lesser than 2 million entries. So let's come to the actual working of it. So how do we start it? In general, we're going to randomly initialize the two matrices with random values and we calculate the value of the boxes. For example here, 1.2 into 0.2 plus 2.4 into 0.5 will yield 1.44, which is less as compared to 3. So we can apply an error function and calculate how much the value generated is deviating from the actual value and accordingly tweak so as to get the value similar to the 1% in the right. For example, 1.44 has to increase so as to come closer to 3. What is the use case of it? As I said in the beginning, the matrix in general in the real world situation will be sparse matrix, that is the few boxes will not be filled. With the help of these decomposed matrix, we can figure out the missing value. For example, Daniel has not rated movie Jaws, but then we can predict it. For example, 1 into 1 and then 1 into 4, it's going to be 5. So Daniel is going to rate Jaws as 5. This is the extensive literature survey done, and one of the possible novel approaches I was thinking about is the plagiarism detector, as both matrix factorization and plagiarism detector has to figure out dependencies and has to come up with a similarity index. So let's see the practical implementation of whatever I've discussed so far. So here I'm going to predict enemy rating using matrix factorization. So the problem statement is clear, as I've said. I've used a dataset from Kaggle naming as ratings.csv and a few studies done on it, like the general ones. The one we have to focus is the training part of it, wherein initially we generate a sparse utility matrix as I've discussed in the video, and later on you use gradient descent cost functions in order to iteratively modify it. And see, after the iteration 800, the mean square error is reduced to 6. And now you can make predictions on the new data. So that now the prediction is almost close, if not exactly, almost close to the original one. And that's it. Now I'm going to hand it over to Niriksha. Thank you.
Hello everyone, this is Niriksha D. Rai. Today I'm here to present a TF-IDF algorithm as part of recommendation system algorithms. So what is TF-IDF algorithm? It uses a frequency of words to determine how relevant those words are to a given document. TF is short for term frequency and IDF is short for inverse document frequency. So TF-IDF algorithm can be used in movie recommendation system, which is an ML-based approach to filtering or predicting the user's film preferences. The formula used in calculating TF-IDF score is the product of TF and IDF, where TF is the number of times the term appears in a document compared to the total number of words in the document. IDF reflects the proportion of documents in the corpus that contain the term. Base 10 log is often used. The computational complexity of TF-IDF is big O of NL log NL, where N is the total number of sequences in a dataset and L is the average length of sequences in a dataset. So till now the algorithm discussed were part of collaborative filtering, whereas TF-IDF is a type of content-based algorithm. Content-based recommenders use data exclusively about the items. For this, we need to have a minimal understanding of the user's preferences so that we can then recommend new items with similar tags or keywords to those specified by the user. As part of the working of TF-IDF algorithm, TF-IDF algorithm involves vectorization by calculating TF-IDF score for every word in corpus related to that document and then putting the information into a vector. Once we have these vectors, we can apply them to various use cases, such as seeing if two documents are similar by comparing their TF-IDF vector using cosine similarity. To show the calculation of TF-IDF scores, I've taken two documents as example with the following term and term counts. To calculate the term frequency of the word this in document 1, divide the term count of this in document 1 by the total number of words. And similarly calculate the term frequency of this in document 2 and later calculate the inverse document frequency of this by by calculating the total number of documents in which the word this has occurred to the total number of documents, and then taking a log to the base 10. So to calculate TF-IDF, multiply TF and IDF for each document. And similarly calculate TF and IDF scores of example in document 1 and 2. And as we can see, the TF-IDF score of the word example in document 2 is 0.129, which signifies that higher the weight signifies that the word example occurs less frequently in the document. This is a comprehensive literature survey on TF-IDF algorithm. So the new datasets used from different platforms like Hotstar has not been explored yet. Also, the features like actors of the movie in the dataset have also been not explored. So such an application for this algorithm has not been worked on yet and is something I'm currently working on.